Hello. Good evening. I'll be right back. I'll be right back. Need a drink. All right. Is this thing on? Okay. I see you guys got some questions. Let's get right on that. Okay. Okay. Can you explain problem 1.2b on final C? Sure. 1.2b. All right, so the question, this is the e-cigarette question. In late 2018, FDA banned flavored e-cigarettes from convenience stores nationwide. The following artificial flavor compounds have been detected in flavored e-cigarette liquid. Okay, so B. Of the three flavors, which has the lowest pKa? So this question is just about, did you memorize the pKa table, which of course can always come up. So you'll want to look at each one of these molecules and identify the most acidic functional group in each. For vanilla, we have this phenol group, which you should know from your pKa table has a pKa of 10. It's a special case when the OH is attached to a benzene ring. But even if you didn't remember that, you might have thought 16. You still would have been fine. NH2, pKa of an amine is 38. And then cinnamon doesn't really have anything except for the alkene protons, which are pKa like 42 or something crazy like that. So the answer is vanilla with pKa 10. Alrighty, next question coming right up is 4F on problem set 6. 4F problem set 6. Okay, let's go to that. 6, 4F. Okay, that is this problem right here. Okay, in the first step, we're going to be treating that ketone. This is 4, right? Yeah, this is 4. We'll be treating that ketone with Cl2 and ACOH. That is the alpha halogenation reaction. Sorry, it keeps changing my pen to the damn fountain pen. I don't want to use the fountain pen. Don't want to use that either. Okay. So what this reaction is going to do, and be careful, very common error in this reaction is to draw this as the product. Very common to draw that as the product, but that is not the answer. Remember that alpha halogenation adds a halogen to the alpha position. So the product after the first step is this. So maybe that's where you got caught up if you didn't put the chlorine in the alpha position. Then NaOH. So this is step 1. Step 2, NaOH is going to do an SN2 reaction on that primary chloride. Give us the following species. I'm just going to abbreviate the benzene ring as pH. Give us this bad boy. And then we treat that with PCC in step 3. Is going to oxidize our alcohol to an aldehyde. Since it's a primary alcohol, it'll go to an aldehyde. Okay, and then we're going to treat that with excess methyl lithium and H2O. And so that's going to add methyl groups to both of those carbonyls, and then on workup we're going to protonate. Okay, so hopefully that clears up that problem there. And so remember that the methyls and the methyl lithium are being added here and here. These are the two new methyl groups. Laura has a follow-up here to the previous question. Wait, why is it doing that? She asks, for the problem you just did with the vanilla, grape, and cinnamon, why do we not take the ester, aldehyde, or the ether into consideration for their pKa's? Because those aren't on our pKa table, and so we don't have values for those. So you don't take them into consideration. You'll notice there's no ester on the pKa table. There is no aldehyde on the pKa table, and no ether either. Okie dokie. So we were just working on the problem set 6, and so we finished this here. Usually step 1 is what gets people tripped up. Okay, next up. All right, a lot of questions about problem set 6, question 6C. So let's take a look at that, and this will address all the questions about 6C. So let's take a deep look at that. I see that someone wanted to do part E for this problem, so I'll go ahead and do that while we're here, and then I'll move on to 6C. So remember, problem set 6 is due tonight, but I give everyone an extension until tomorrow night. But please just turn in problem 6 tonight. Don't be forgetting to turn in a problem set. Okay, let's do E. So the first step, we do ozonolysis. That's going to cut up our alkene into this ketone. Then NABH4 methanol is going to come along and reduce our ketone to the alcohol. H2SO4 and heat on a secondary alcohol will do E1, dehydration of alcohols reaction, to form an alkene. And then another ozonolysis reaction will chop that alkene up. I'm just going to abbreviate pH to give this aldehyde. That aldehyde is then treated with Jones's reagent to give the carboxylic acid. And then the carboxylic, remember, aldehydes react with Jones's reagent to form carboxylic acids. And then that is treated with SOCl2 to give us the acid chloride. So that should be the right answer for that one. And yes, just to be clear, primary alcohols will never do E1 reactions. They only do, as the major product, industrial ether synthesis. So if you have a primary alcohol that you want to turn into an alkene, in this case, we didn't have a problem because we had a secondary alcohol, so we could use H2SO4 and heat. But if you ever have a primary alcohol, that is an alcohol that has one alpha carbon, an alcohol that has one beta carbon. This alcohol is secondary because it has two beta carbons. Then using H2SO4 and heat is going to do the industrial ether synthesis, not make the alkene. So if you want to turn a primary alcohol into an alkene, you'll need to convert it into a good leaving group, for example, with tosyl chloride pyridine, and then do E2 with KOTBU. All right. So let's go on to 6C now. I know that's a big topic here, so let's go on here. All right. So I'm just going to erase this here because I was working this out with someone else. Okay, so the first thing to do when you see this problem is don't freak out. Okay, it looks huge, it looks scary, but really it's not that hard if you break it down. And so when you have big molecules like this, it's best to work your way from the outside in. Okay, that's my suggestion for you. So looking at this big molecule here, we're going to start with the outside and just work our way in. We see esters here. And so one of the only ways that we know to make esters, right? So if you ever see something like this, you have esters, is from the alcohol. So chop this bond here and make alcohols at the connection points for the ester. So reversing our retrosynthesis here. It may be difficult to see because we did just learn these acid chloride or ester reactions, we don't have so much practice using them. So we have some challenges when it comes to making esters. And so it may not be immediately obvious that if we just took this molecule here and treated it with this molecule in the toolbox, we instantly get the product. And seeing this molecule here, well, that's pretty easy to make from this starting material here, the diester, because we see we've added a total of 4 methyl groups, and we know that esters react with organometallics to add R groups twice. So we can revert that as well. Again, working our way from the outside in. I just know I'm going to run out of room. Move that over there. So really, if you can get to this stage, you're basically done. And it's really not that hard here, because now the next thing you see is, well, this is almost exactly the starting material, except for the Diels-Alder reaction. We see that six-membered ring, so we go ahead and revert that Diels-Alder reaction in a retrosynthesis. Again, these types of problems are much easier to work in reverse. And so if we undo the Diels-Alder reaction, since we have a cyclohexadiene, it's clear that it was made from an alkyne plus this starting material here. Okay, so then now this material is something we're allowed to start with in our toolbox, but this guy is not. So now we just have to make this. It's an amide. And so the best ways to make amides are if you just take a carboxylic acid and an amine, heat them up together, and you'll get an amide in a single step. So let's take a look at our starting materials. Oh, what do you know? We have a carboxylic acid and an amine. We can just react these two together with heat, and we would get that immediately. And so that is the complete retrosynthesis. So that just doing these steps, you'll see it's really not that bad. You mix these two together, you mix these two together, then you get this. This is just simply reacted with 4 equivalents of methyl lithium to get this. And then those alcohols are easily converted into the esters by treating them with the acid chloride. So it's really not so bad if you work your way backward and not be intimidated by the large footprint of the molecule. All right, so I won't go through the forward synthesis. You can see that on the key, but that is the retrosynthesis. All right, let's see where we are at. We're up to bonus problems 9, question number 3. A lot of questions tonight. I'm very happy. How many viewers do we have? What does it say? 67. Hey, that's pretty good. All right, bonus problems 9. All right, let's take a look here. It's always fun to jump around. So fill in the blanks. Well, how did we get from here to here? It looks like we just added some carbons to the less substituted side. So for that, we're going to go ahead and use our old friend, the organometallic reagents. So metallic here. In step 2, we'll need that H2O workup. That's going to go ahead and give us the first product, right? Because again, the mechanism here is that we just have the epoxide being attacked by the organometallic. And then now in the second step, this is what you asked for. Br2 and H2O makes a bromohydrin. So that's going to add bromine to the less substituted side of the alkene and OH to the more substituted side. So that's going to give us this. So we end up with a OH on the more substituted side and a bromine on the less substituted side. Now, technically, those would be anti to one another, but we don't really care about the stereochemistry because the bromine is not on a chiral carbon, and now we're treating this molecule with PCC. What is this molecule going to do when you expose it to PCC? Well, we have a tertiary alcohol that does nothing in the presence of PCC, and a secondary alcohol that'll become a ketone in the presence of PCC. So we're going to go ahead and add in our ketone, and that's the final product. We're done. Next up. I'm going to be checking periodically the end of the chat just in case you guys have a question. Okay, so 7D from Practice Final C. Here we go. Oh yeah, this one was so good. People were absolutely dying with this one. I saw so many people just dying on the inside. So that made me very happy. Not that people were struggling, but that I come up with a hard problem. I'm not like sadistic like that. But it's good to see people being challenged. And so in this reaction, we're adding 2 equivalents of ethyl magnesium bromide to an ester. So remember, that's going to add twice. You know, the first equivalent adds up here, kicks electrons up. And give us an O minus. Electrons are going to come down off the O minus and kick out this oxygen as a leaving group. Remember, this is how the addition of organometallics to esters works. One, two, three, four, five. 1, 2, 3, 4, 5. O minus, and then another equivalent of the ethyl magnesium bromide adds. Whoop. Okay, so then we get a molecule that looks like this. So we've added 2 R groups to our carbonyl. And then now there should have been a workup. I made an announcement at the beginning of class that there needed to be like an H2O workup here. So this is step 1.5. But even if you didn't have that, look what's in the second step, H2SO4 and H2O. That's going to provide protons immediately for these O's. And so after we treat that with the Jones's reagent, I'm just going to go up here. Well, we have a tertiary alcohol, so that won't be affected. But then we have a primary alcohol, which will be oxidized to the carboxylic acid. Okay, and then we treat that with SOCl2. That'll turn the carboxylic acid into the acid chloride. Remember that SOCl2 doesn't do anything to tertiary alcohols. It only works with primary or secondary alcohols. So everyone should be able to get to this stage of the game. This isn't too hard. Okay, but then this is the hard part. I gave this hint. Answer contains formula C8H14O2. So everybody was freaking out because of that formula, because isn't the answer supposed to have a chlorine in it? I thought the answer was supposed to have chlorine in it. So everyone thought, oh no, it's another typo. It's another typo, just like over here he made a typo. But actually, remember, if you have an alcohol and an acid chloride in the same molecule and you started seeing these neurons started clicking and people started figuring it out, that now this OH is going to do alcoholysis of acid chlorides, kick out the chlorine. Okay, and then that's going to go ahead and give us the molecule shown. Okay, so and after it does an intramolecular alcoholysis, you get the following ester. You remake the ring. And if you have trouble seeing the ring, you can go ahead and number the carbons in oxygen. So 1, 2, 3, 4, and 5. You know that you're going to be making a 5-membered ring. So 1, 2, 3, 4, and 5. 5 has the carbonyl. 2 has the 2 ethyl groups. So that's how you get to the ring. Next up, that's a real good one. Next up, 5B from practice final A. So this one was a little bit, here's the answer to this one. This one was a little bit annoying because this is from a different class where they used NaH to deprotonated alkynes, but in this class we use NaNH2. So I'm sorry for the confusion. I meant to update this. So NaNH2 is synonymous with NaH. If you want to deprotonate alkynes with NaH, you can, but this is what the other class was using. And so we deprotonate the alkyne to give the acetylide anion. That adds to formaldehyde to give the following new carbon-carbon bond, and then that O- gets protonated by workup to give the alcohol alkyne, and then H2 Lindlar reduces that alkyne to the cisalkene. Could you go over the mechanism for 4E in problem set 6? Did we already do that one? Yeah, we did 4E. Problem 4B on practice final A is next. Uh, 4B, is that? Is that this? So I'm going to try and not do the mechanisms just because they're too time consuming, especially this epic mechanism. But let me see if I have... If there's time at the end, we'll go back and do this one, okay? But the answer key is there, so you can just follow the steps. But essentially, we protonate the carbonyl oxygen. One of the alcohols adds the carbonyl oxygen. Doesn't matter which one. We remove that pesky proton and neutralize the charge. And then we're going to go ahead and protonate this original oxygen. The other alcohol of the diol is going to attack the carbonyl, another proton transfer step, and eject water out. And, you get to the product. So you can see the mechanism for that. If there's time at the end, we'll go over it. Bonus problems 8, question 1F. How do you connect the thiol? Bonus problems 8. Which one is that? Hold on a sec. Bonus problem 6. It's the one with the aldehyde. Okay, sorry. This dust in this air is killing me. I'm doing construction on my roof. Question 1F. How do you connect the thiol? I'm going to just erase this here. All right, so what you notice in this problem here is that we have absolutely added a thiol to our molecule, and in order to add a thiol, that's a dead end group. So to put those in, you need a good leaving group. So if we kind of do a retrosynthesis here, you could replace the thiol group with OTS, not worrying so much about stereochemistry here. And then remember we talked about using dead end groups, and then the OTS in our retrosynthesis would then become an OH group. And then now this appears to be the product of a Grignard addition to an aldehyde. And so that's going to be our forward synthesis. So it's going to be step 1. We're going to do PHLI. So that's going to, and then step 2, we need that H2O workup. So after we do that, we're going to end up with this. Go ahead and turn that OH into a good leaving group with tosyl chloride pyridine. You could also do HBr, the old school method. Variety of other methods will work here. And then step 4, so that if we do that, that's going to make our OTS. And then to get to this product here, now we just need to do SN2 or SN1. So we can just do like HSET, and that'll do SN1. Or you could do SN2, since you do have this tosylate is both wedge and dash, because the addition of the organometallic is giving you a racemic mixture here at this stereocenter. So even if you do SN2, you're going to get the same product. So you could do NaSET. That would also be full credit. Okay. Does AlBr3 not need to be explicitly written? I'm not sure the context is on that. Julia, if you let me know which reaction you're thinking of with AlBl3 does need to be explicitly written. That's not optional. So mechanism from the last of the LA review worksheet. Yes. 4C. The crossed aldol reaction. So in this reaction, this is 4C, right? Oh, no. This is 4C. Okay, so the mechanism of this is going to be, oh, it's going to be kind of a long one. Okay, here we go. So we have the chlorine attacks the aluminum of the AlCl3. This is the first step of our Friedel-Crafts reaction. That goes ahead and gives us this complex where the aluminum has a negative charge, the chlorine has a plus charge. Okay. Julia, I saw your follow-up comment. We'll go back to that in just a second. Okay. Then in this stage, the electrons come down off oxygen to kick out the chlorine. This is to form the acylium ion. Here's our acylium ion. Then the benzene ring is going to do an intramolecular attack of the acylium ion. Remember, if you form an acylium in the presence of a benzene, if it can form a 5 or 6 membered ring, it will. So that's going to go ahead and form this. Carbocation on the 6 o'clock carbon. And then the aluminum tetrachloride is going to act as a base. To reform the aromaticity, and then that leads to the product. And so that's the mechanism. Just a Friedel-Crafts acylation mechanism that happens to happen intramolecularly. I think there's also one of these on the problem set. Not the problem set. The practice final C, one of the mechanisms on that practice final is very similar to this problem right here. It could not attack para because it would be too far to reach, right? And it would make a 6-7 membered ring, which is not favored. So because it's hard to reach, and also because the ring would not be 5 or 6 membered ring, para would not be favored. So the 5 membered ring would be favored. For intramolecular reactions, you typically are going to be attacking ortho only. For the purposes of this class, if you do an intramolecular Friedel-Crafts reaction, whether it's alkylation or acylation, it's always going to go ortho. It'll never go meta or para. Just going back now to follow up on Julia's question about the problem set 6. For 6, how do you know that it would form the acylium ion? Because that's the mechanism for the Friedel-Crafts acylation, right? Every Friedel-Crafts acylation forms the acylium ion. Okay, so I think the question was here, why did you abbreviate the AlBr3? That's only for the Friedel-Crafts reactions. This is not a Friedel-Crafts reactions. Remember, acid chlorides, yes, they react with benzenes in the presence of AlCl3, but they also simply react with alcohols, and in that case, you don't need any aluminum catalyst. They just react with the alcohols directly to do alcoholysis. Okay, so remember, acid chlorides, when you're trying to add them to a benzene ring, you need the aluminum, but when you're trying to add acid chlorides to alcohols, water, or amines, no aluminum is needed because you're not adding to a benzene ring. It's another reaction of acid chlorides. All right. Next up. What's the difference between acid and mercury catalyzed addition of H2O to alkynes versus hydroboration oxidation of alkynes? Usually, the hydroboration oxidation of alkynes forms aldehydes, and acid and mercury catalyzed addition of H2O makes alkenes. So, for example, if I have the following alkyne, if I treat that with step 1, CY2BH, step 2, H2O2, NaOH, H2O. We're going to go ahead and make an aldehyde. Because this is adding OH, the less substituted side of the alkyne. One sec, got to blow my nose real quick. I deeply apologize. Okay, next we're going to do the acid and mercury catalyzed addition of H2O. That's going to add to the more substituted side, and so we'll end up with a ketone. So the difference is the hydroboration oxidation is non-Markovnikov, And the acid and mercury catalyzed addition of H2O is Markovnikov. All right, hope that clears that up. All right, next up. For practice final B, page 8, problem D, where do you place the alkene? This is page 8, problem D. Remember that in the aldol condensation reaction, the alkene always collapses towards the carbonyl. So let's take a look at this reaction. So this is an intramolecular aldol to start. So let's go over the steps of that. So remember, to start this one off, you go ahead and want to draw in all the alpha hydrogens. And there are all the alpha hydrogens. And then we go ahead and arbitrarily number our carbons. And we have 6 carbons in our molecule, 1, 2, 3, 4, 5, 6. And we're going to go ahead and make a list of all of our alpha hydrogens. So we have alpha hydrogens on 1, alpha hydrogens on 3, alpha hydrogens on 5. And we're going to go ahead and count to the nearest carbonyl. So starting at 1, 1, 2, 3, 4, 5, 6. That's pretty good. That's 6-membered ring, counting towards aldehyde. Starting from 3, we have 1, 2, 3, 4. That's a 4-membered ring, counting towards aldehyde. And then starting from 5, we have 1, 2, 3, 4. That's a 4-membered ring, starting from counting towards, sorry, was I say starting from? Counting towards aldehyde, and now we're counting towards a ketone. All right, so now we know that number 1 is our winner because we're making a 6-membered ring, and that's the favored size. So we're going to go ahead and draw a 6-membered ring now. And go ahead and number the carbons inside that ring arbitrarily. So 1, 2, 3, 4, 5, and 6. Okay, I see that carbon 4 has this lovely square on it, so I'll go ahead and add the square. 1 is attacking 6, so 6 is going to have the OH group. And then 1 is going to have nothing. 2 is going to have the ketone. And so that is the product after step 1. Then now we do the heat, and this was where we got to your question. Okay, so Zaitsev's rule does not apply to the aldol condensation. All that matters is that the alcohol needs to collapse for the alkene to form towards the carbonyl. That means towards 1 and not 5. The aldol condensation always forms towards the carbonyl. And the reason is, if you remember back from 14Z, do you remember the word conjugation? It was talking about how double bonds that are conjugated with each other are more stable. There's a lowering of energy. So that is the reason why the aldol condensation always puts the alkene towards the carbonyl, because that's more important to be conjugated than to obey Zaitsev's rule, for example. Conjugation is a huge energy savings. So that's sort of a connection to 14C. Then OSO4, H2S, is going to go ahead and make the cis diol. Okay, and there's your final product. Okay, 5.1C of practice final B. This is the acetal formation reaction. So if you ever see a ketone plus an alcohol in H2SO4, you're going to form an acetal. And so if you see now we have a diol, that means we're going to form a cyclic acetal. So the product is very easy to draw. Just draw the ketone. Okay, and this is what I like to do, to draw the ketone, and then the CO double bond is going to split into 2 oxygens. Just like this, oxygen, oxygen. And then now we're going to go ahead and make sure that we have this alcohol connected up there. So we have a 1, 2, 3 carbons connecting the oxygens. So that's going to be like that. And make sure you can draw the mechanism for that reaction. That's the mechanism. If there's time at the end, I'll be able to go over that. Sorry, blow my nose again. You would not be surprised how much dust comes off of a roof. I mean, yeah, you would probably be no, you would not be surprised. I was right the first time. Let's see here. Next up, we have can we use a reagent for Friedel-Crafts alkylation in a synthesis problem if it's not in the toolbox? No. Unless the problem says that you can use carbons of 2 or less, you cannot use carbon-containing molecules outside the toolbox, because that is a carbon-containing piece. For final C, question 5.1e. Okay, so in this reaction, LiAlH4 is going to go ahead and reduce the carboxylic acid to the primary alcohol. And then H2SO4 in heat for primary alcohols makes symmetric ethers. Remember that H2SO4 in heat with primary alcohols makes symmetric ethers. H2SO4 in heat with secondary and tertiary alcohols does E1. So that's just a memorization thing. We already did that one. Are there any mechanisms besides EAS that we cannot use generic bases to deprotonate? I made a list on the June 3rd lecture notes, I think on page 2, of reactions that you cannot use generic bases for. So that's lecture notes 6.3, page 2. So for that, the only other reaction that you can't use a generic base for is E2 reactions, deprotonation of alcohols, and deprotonation of alkynes. Practice final exam B, question 7D. How do you know where the OH is on the benzene? Okay, so a few issues here. Remember that we just worked out this problem, and there's no benzene in this molecule. Remember, just because there's a 6-membered ring does not mean that's benzene, okay? That does not mean that's benzene. This is not a benzene. In order for it to be benzene, it needs to have 3 alternating double bonds, okay? And how do you determine where the OHs are? Well, first you have to determine where the alkene is, and for that you need to know how to do the intramolecular aldol reaction. So we kind of did work through this already. So you should have your answer now. Okay, practice final B, question 1.1, ranking task, coming right up. Oh, 1. So benzene had no role here, so we're just going to go ahead and rank these. The acid chloride, we know, this is just straight memorization, is the most reactive, followed by the anhydride. Next we have the ketone, and then finally the carboxylic acid. So we're not actually caring about the benzene ring. All we're caring about is what's attached to our benzene, what's attached to our carbonyls. That's defining what sort of functional group it is. I would not ask you to compare, for example, this would be a very hard comparison. Which is more reactive, this carboxylic acid or this carboxylic acid? They're going to be very similar because they're both carboxylic acids, the only difference being the benzene ring. It turns out that the benzene ring is slightly electron withdrawing, which would make this carboxylic acid slightly more reactive than this carboxylic acid. But I would not ask that question on the final. It's going to be very clear and very simple. The list to memorize is in the lecture notes, and it is on, let me see which page that is on. The list to memorize. Stand by. Not that one. 524. not 529. Oh yeah, it's the end of 524 lecture notes. Last page of 524. All right. Next up, where are we here? For final C, question 10.1, can you go over the intramolecular aldol condensation? Yeah. All right, so let's see. The intramolecular aldol condensation happens in step 2. So again, this question here, there's going to be a weird question like this on the final with all of this just bizarre text. And I just want you to remember that don't be scared by all of this text. Most of it is just there to distract you. In fact, in this whole thing, there was only one clue in the whole thing, which was just bridged bicycle. Okay. After that, you just ignore all of this bull crap. It was slightly funny. And then you get down here to the actual problem, which is just, you know, I could have asked this without any of that crap. It doesn't matter that we're synthesizing a made-up drug. Okay, so let's go ahead and do our ozonolysis reaction. So that's going to lead us to this molecule here. Okay, and then now we need to do an intramolecular aldol reaction. So we'll go ahead and draw in our alpha hydrogens. There's 3 of them, so we'll want to go ahead and arbitrarily number our carbons 1, 2, 3, 4, 5, 6, and 7. And so we have alpha hydrogens on carbons 1, 3, and 6. We'll want to determine the ring sizes for each one of those. Okay, so starting from carbon 1, counting to the nearest carbonyl, 1, 2, 3, 4, 5, 6, 7, 7-membered ring, that's not great. And we're counting towards an aldehyde. We're counting towards the aldehyde. For number 3, 1, 2, 3, 4, 5, we have a 5-membered ring, and we're counting towards an aldehyde. And then for 6, 1, 2, 3, 4, 5, another 5-membered ring towards the nearest carbonyl, counting towards a ketone. So we have a tie there. And so number 1 obviously loses because 7-membered rings are not favored. So it's between 3 and 6. 3 is counting towards an aldehyde and 6 is counting towards a ketone. It's much better to count towards an aldehyde than a ketone. So 3 wins. So we're going to connect 3 to 6. We're going to connect 3 to 7. 1, 2, 3, 4, 5. 3 to 7 is what we're connecting. So we'll go ahead and draw a 5-membered ring. And go ahead and number the atoms inside that ring, 3 through 7. So 3, 4, 5, 6, and 7. And go ahead and decorate that ring. So 3 is connected to 2 and 1. So there's 2 and 1. And then 7, we just attacked it. It's an aldehyde. So we have an OH group on there. Okay, so that's how we get to the intramolecular aldol product, but this is an intramolecular aldol condensation, so we're going to go ahead and erase that OH and make sure it's an alkene. And so that's our final product. Now, another part of your question is, why? I thought aldehydes were preferred. You're mixing it up, okay? It's preferred to attack the aldehyde, which means there's not going to be an aldehyde left over in the product, because once the aldehyde gets attacked, it becomes an OH group. So it is preferred to attack the aldehyde, but it's actually preferred to have a ketone left over in the starting material, okay? That's a very important distinction, okay? It's preferred to attack the aldehyde, but that means there won't be an aldehyde in the product. So when you say aldehydes are preferred, that's true. Aldehydes are preferred to be attacked, but not end up left over in the product, okay? Hopefully that's clear now. We'll go ahead and continue now. So we're going to do a Diels-Alder reaction on that. So if we go ahead and do a Diels-Alder reaction, we're going to go ahead and have the 5-membered ring making a 6-membered ring connecting to it. And that is going to have the alkene over here on this side. I think actually in the answer key, I'll draw it like this. I put the 6-membered ring on the left side rather than the right side. So just to be consistent, I'll do that. But keep in mind that it doesn't actually matter. And then where's our whatchamacallit, our ketone? Well, if you recall, this was originally our alkene of our dienophile, so our ketone is now up here on the molecule. Okay. Good so far? Everyone good? Everyone hopefully following so far? Okay, now we're going to do NABH4 methanol. NABH4 methanol. So remember, just to be clear on this Diels-Alder reaction, so I'm just going to kind of draw my... Oops. I'm going to just draw my ketone next door to my dienophile, and so we're going to be connecting these here, and so I'm just going to draw the... Right, and so that's how we get to the product, which looks like this. Okay, next we're going to go ahead and reduce our ketone. So now we have this structure here. And then now Br2 and CCl4 is going to go ahead and create the dibromide. I'm sorry. I knew I was making a mistake here. The ketone is not on this position. The ketone's on this position. I knew something was off. Right, because if you look back here, right, the ketone is actually, this is not the right position of the alkene. The ketone is actually here. Sorry about that. Right, it's a conjugated alkene, right? So this is carbons 1, 2, 3, 4. Oh, sorry, based on my numbering. 1, 2, 3, 7, 6, 5, 4. There we go. Okay, so this is not the right product. Sorry about that. Okay, we get to this product here. Then we're going to reduce the ketone down to the alcohol. And then now we do Br2 and CCl4. That's going to form the bromonium ion. Just like this. And then this does an intramolecular haloether forming reaction. So the oxygen is going to attack, open up the bromine, and that's going to create the bridged bicycle. So this is very similar to one of the problems on problem set 4. I think it's like 2I or something like that. And so that's going to give us this product here, bridged bicycle. Okay, so that's how you do that problem. Just make sure that you don't get confused when you draw the Diels-Alder product like I did. Oops. All right, moving right along. Next up, we have, where were we? How would you add a single methyl to a benzene? Extra synthesis extra practice problem, bonus problem A. You could just do the Friedel-Crafts alkylation. I said in the class you can ignore polyalkylation. So just take a benzene and then methyl chloride AlCl3. That'll put a single methyl on a benzene. You can ignore polyalkylation. Will we have to rotate dienes and assists for the final? No, we will not. And then, yeah, related to the other one, you can use Friedel-Crafts alkylation and synthesis problems even though it leads to polyalkylation. Yeah, and I did skip the deprotonation acid base step because I didn't feel like drawing this molecule again. But remember that there is a species here with the O has a plus charge, and then that's going to get deprotonated before you get to the final product. So if you were actually drawing the mechanism for this, you would be expected to do an acid base step. But since we were just trying to predict the product, I was just showing how it forming. Let's see. We kind of talked about this already. Could you use NaH for deprotonation of a terminal alkyne? If yes, is it because it's a strong base? Yeah, and in some of the other courses of 14D, they used NaH to deprotonate alkynes. But in this class, I use NaNH2. For this question here, we had answered this earlier, so rewind if you didn't get your answer. Does acetone need to be explicitly stated for Jones? No, it's an optional solvent. Practice final C, number 8.1b. After splitting the molecule in half with LaAlH4, can you 1. Apply PCC to the pentane ring, 2. Add Br via halogenation of ketone, 3. Reprotonate the ketone? Oh, I see. You want to add the bromine by alpha halogenation, then not reprotonate, but reduce the ketone back to the alcohol. Reprotonate the ketone. I'm just not sure about step 3. If you have an alternative synthesis, send it to me and I'll. Oh wait, you have more. Oh no. Okay, so you're gonna lose a point if you do it this way. Why? Okay, so basically what you're proposing is this. Yeah, so I see there is a problem with this. So what you want to do. You're close. I would give you most of the points. I'd probably take off 1 point only. But what you want to do is you want to take this ester. I'm just going to do exactly what you say. And you're going to treat that with step 1, LiAlH4, step 2, H2O. And that's going to give you 2 alcohols. Give you this alcohol plus alcohol. Remember that LiAlH4 and an ester is going to give you with 2 alcohols. Okay. Now what you're saying is take the pentane ring and do PCC with that. That's going to give you the cyclohexanone. Then you want to put on the alpha halide. So Br2ACOH. Okay, then you want to reduce with NABH4, MEOH. That's going to give you this. But now here's where the problem happens. You want to treat this with step 1, NaH, and then step 2, you're going to like turn this into a bromide or something with PBr3 or whatever and try and do a Williamson ether synthesis. But look what's going to happen. You're going to make this, and before it can do an intermolecular Williamson ether synthesis, it's going to do an intramolecular Williamson ether synthesis, and this is one of the ways we know to make epoxides. You're going to end up making this epoxide here. So you're not going to actually get to the right product because intramolecular reaction is going to be favored over the intermolecular reaction. So I would still give you most of the points, maybe like 5 out of 6 points, but you're going to lose a point because intra is favored over intermolecular reaction. Okay. Will the reaction of an acid chloride and carboxylic acid give us an acid anhydride? It does, but we didn't learn this reaction in the class, so you won't see it on the final. Can you go over 7A on final C? Okay, this is final C, right? Yeah. Okay, so first step, we're going to do the cyclohexylborane. So that's going to give us the 1, 2, 3, 4 carbon aldehyde. Like this. That's after step 1. Then we're going to do an aldol reaction with a crossed aldol reaction, I should say, with that carbonyl in step 3. So that's going to lead us to this. Sorry, a little messy there. And then treating that with PCC. Oh, sorry, this is an H here. Treating that with PCC is then going to oxidize the secondary alcohol up to a aldehyde. I mean, to a ketone. And that'll give us that product. So we get 2 carbonyls in the end. So I think the hard part here is seeing the crossed aldol reaction. So remember, the mechanism is just we're going to be taking one of the alpha hydrogens off. So we have OH minus. I'm taking that proton, putting a lone pair there. And then that anion is going to add to our non-unilizable carbonyl, which is this aldehyde. Tacks up here, kick electrons up. After a protonation step, that'll lead us to this product here. Can you go over the first step in 8.1b? How does LiAlH4 cause the starting material to split? So that is back over to here. Remember, if you add LiAlH4, it's going to reduce the ester to a primary alcohol, and you're also going to be left with the ester part as a leaving group. So you end up with both pieces that you can then use in the synthesis. Remember that all the ester reactions produce 2 products, and you can use one or both in synthesis. So if you treat an ester with LiAlH4, you get 2 alcohols out, and you can use both of them. And so I think that also answers Kayla's next question. So again, one of the things you can recognize in this is that the starting material here, you have one starting material, but it ends up sort of split up in the product. And so you have to use carbons from both sides of the ester. That's pretty tricky. Question. Can we use MCPBA if it is not in the toolbox for a synthesis? The answer is yes, because even though it contains carbon, it doesn't add carbon, so it's fair game to use it. Only if it were to add carbon would it not be allowed. Next question. Problem set 6b. Why did you use reduction of aryl ketones in aldehydes? Not sure which. 6b? 6b? I'm not sure which problem you're referring to here. Problem set number 6b. Oh, synthesis 6b. So your question is, why did you use the reduction of aryl ketones in aldehydes? Could we not have left that there after doing the, have gotten the final product? Okay, so if you leave the ketone here, so you're doing this a different way. Oh, is this maybe this is not the answer that's the same as on the key? I may have worked it out a different way here. Let me see what's on the keys. This is actually the key. Oh yeah, okay. So, oops. So first we put on the ketone. If you don't reduce it when you do the next reaction, it'll go meta because ketones are strong deactivating groups. But we want the new group to be para. So that's why I reduce it down to the alkane, which is a weak activating group, which will go para. And then now we still have the weak activating group is the strongest activator on the ring. So the subsequent reaction to add the NO2 group will go ortho now that the para group is blocked. And then now we use Jones to reoxidize that carbonyl back to the ketone. So it's a matter of getting the wrong regiochemistry if you do not remove it. Julio, just to comment, you making a comment about this, why not get rid of the bromine before reducing the carbonyl? Well, you need the bromine in the target product. So if you have an alternative solution that involves getting rid of the bromine and then restoring it, go ahead and let me know. But you need the bromine in the target product. So you don't want to get rid of that. Okay, midterm 2, 5C. Oh, midterm 2, huh? Where is midterm 2? to really look for that one. I wasn't expecting questions to come from that. Hold on. Here it is. Wide is using, okay, midterm 2. Think about this one here. So if you do NaNH3 H2O, you're going to get the transalkene like this. And then if you do OSO4 H2S, you're going to get that adds 2 OHs cis to one another. So you're going to get this product here, but that's not what was desired. We wanted the trans product, so you can't use that sequence. But if you go through the cis-alkene, then it's okay, right? Then you can use the OSO4, because what you'll do is you'll make the cis-alkene, then you'll do the OSO4 reaction, you'll get to this diol. And then that, after you rotate it, is the target product. Right? After you rotate around the single bonds, the carbon-carbon single bonds, you get to the target product. For intramolecular aldol condensation, we prioritize the number of sides to the ring. So making a 5 or 6 membered ring is the most important thing. And then if there's a tie, adding to an aldehyde is better. I'm not sure which you were referring to, but dichloromethane is typically a non-participatory solvent with ozonolysis. So if you see CH2Cl2, it's always just a solvent. Sharon, if you have other alternative synthesis, just email it to me. I'll check your synthesis. Can you explain 8.1b on final C? I think we went over that one. That was a real tricky one, right? That's the one where we splitting the so let me just go over the right way to do this problem, okay? Because I know this one was tricky. So the right way to do this problem is to really start with the product and recognize what special functional group do we have in the product. We have a halo ether, right? And so in order to form the halo ether, we take an alkene and treat it with Br2 plus an alcohol. Sorry, having trouble drawing the triangle here. Right, so if you have an alkene plus Br2 plus alcohol solvent, you'll make a halo ether. So that was the key to solving this problem. So it's actually pretty easy once you recognize that. So all you have to do is treat this with step 1, LiAlH4, 2, H2O. That'll give you the 2 alcohols. Okay. Now this guy here we're going to use later, but for this alkene, then we're going to turn that into that alcohol, we want to turn that into the alkene. So H2SO4 heat, that'll work because it's a secondary alcohol. That'll go to the alkene. And then we just treat that with Br2 and HO, this thing. And that's going to lead to the... I told you didn't have to worry about stereochemistry. So that leads to the product in a single step. Nice, right? Not so bad once you recognize the halo ether, right? MO, the bridge bicycle one, we did that one in fully. Can you go over the one trick? Can you go over the trick again about when you protonate the leaving group? So that was talking about ester reactions. And so what we said was that, let me just find that in the notes here. That was in the womb. So the rule is that there's a few reactions in that chapter 19 and 20 that involve carboxylic acids and esters as starting materials. And there was 3 main categories of those reactions. There were acidic reactions that contained H2SO4. For example, if you have an ester and you treat it with H2SO4 and water, that's going to make a carboxylic acid. That's called ester hydrolysis. If you see H2SO4, you know it's acidic conditions. So in the mechanism, you'll want to protonate the carbonyl oxygen and the leaving groups before leaving. Then there's the neutral reactions. The giveaway for that is the presence of RNH2. In that reaction, you don't protonate the carbonyl, but you do protonate the leaving groups. And then finally, some of the reactions are basic. You know it's basic if you see sodium, lithium, or magnesium. You don't protonate either the carbonyl or the leaving groups. So we can go through and look at some of those reactions and see that this works. And again, this is a trick for helping to memorize the mechanisms for these reactions. So this reaction you can see is base catalyzed. So if you see, because we see Na, so we know this is basic conditions, so we won't protonate the carbonyl, and we also will not protonate the leaving groups. This reaction here, acid catalyzed ester hydrolysis, it's acidic conditions, so we protonate the carbonyl and we protonate the leaving groups before they leave. The acid chloride reactions are a little funny. We never protonate the carbonyl and we never protonate the leaving group if the starting material is an acid chloride, so you just have to kind of remember that separately. So let's see, here's one. Acid conditions, I see H2SO4, so we protonate the carbonyl and we protonate the leaving groups. Aminolysis, this is a neutral one, so we don't protonate the carbonyl, but we do protonate the leaving group. So here's the leaving group leaving. Oh, sorry, I'm looking the wrong way. Okay, so we do not protonate the carbonyl, but then we do protonate the leaving group before it leaves. Basic conditions, we see the lithium, don't protonate, don't protonate. And again, another basic one, we don't protonate the carbonyl before the nucleophile adds, and we don't protonate the leaving group before it leaves. Andrew Melendez, I did go over that full problem. I kind of botched it up because I put carbons in the wrong place, but if you can forgive my error there, then I did go through the whole thing for, I think you were referring to the Acorna problem. This thing here. So if you rewind, I went over all the steps here. Sorry about the error for earlier. Let's see, next. Just a few more questions left, and then we are over time, so we're going to go ahead and call it. For bonus problem 517.19.3a, is it okay to add Br before Friedel-Crafts alkylation? Let me just see which one that is. Bonus problems 517.3a. Yeah, the order of 1 and 2 and 3a doesn't matter for that one. Let me see if I can find that one. So that's this bonus problems here, and then 3a. Oh, no. The order does matter, right? You want this product selectively, so we're starting from this compound here. We want to add the alkyl groups to the para position, so whatever you do first is going to end up at the para position. If you do Br before Friedel-Crafts, then the Br is going to end up down here, and you don't want it there. You want the isopropyl group there. So we can go ahead and do AlCl3. That's going to go ahead and give us this. Step 2, Br2, FeBr3. That's going to, now the para position's blocked, so it's going to go ortho to the strongest activating group, which is still the NH2 group, which is a strong activator, and the isopropyl group is a weak activator. So NH2 group wins, and so it's going to go ortho to the NH2 group. Okay, and then we just want to turn that NH2 group into an NO2 group, so TFPAA will do that, and that'll lead us to our final product. Always para first for this class. Always para first. There's actually some reactions where ortho is favored over para, but we didn't have time to get into the details of that, so it's very complicated. There's people have devoted their entire careers to understanding ortho selectivity in EAS reactions. Huge field, no way that we would have enough time to do it justice. So we're just doing with what is most commonly observed, which is that para will occur preferentially unless the para position is blocked or it's an intramolecular reaction, in which case ortho will be the second best choice. How does the class usually do on the final relative to the midterms? I don't know. Let's see. What was the average last quarter? I'll tell you. So last quarter, the average on the final was a 118 out of 160, which is a 73%. So about the same. People normally do about the same on the final as they do the midterms. The averages are, for the midterms, have ranged between 70 and 80, and same with the finals, always between 70 and 80, usually somewhere close to 75. All right. All right, guys, thanks so much for all your questions. I'll be checking my email and Q&A questions as frequently as possible, within reason. So thanks for joining me, and I will... Oh, is there one more question? Okay, one more question. For both Friedel-Crafts alkylation and acetylation, can we use BR instead of CL? And if we do, change AlCl3 to AL? Yes. So if you want to use, as your first step, this, you're fine to do so. That would also work. Just make sure that they match, okay? Just like the halogenation reactions. All right. Good luck, guys. I'll see you all tomorrow. Bye for now.